along and speak to you this afternoon. And I'm Technical Director at Light Science Technologies, and we are a company that works very much in the development of technology for closed environment agriculture. This obviously includes vertical farming. I just need to click on here and we should be able to start going. So we create affordable bespoke solutions, and they include all sorts of sensors, and we'll come to some of those in a bit. We're a company that is, in fact, just floating as a PLC. So we have in a group Light Science Technologies, which is run from our offices at Hilton in Derby, where we have a research laboratory. We'll talk about that in a bit. We also own a company that's in Manchester as part of the group called UK Circuits, where we manufacture all of our projects. So all of the electronics is UK manufactured. We like to keep it in the UK if we can. We have much better control and quality for those products that we're building. We add value to our customers really by looking at light and recipe of the environment and the lighting, and then we monitor and support it. So we're looking at products that not just sort of 4 or 5 years worth. We're developing products, and we have products in light now. So lighting, you typically expect them to last around about 4 or 5 years. We're around about 95% totally recyclable our products, and 80% of it's reused difference, and they're cost competitive. What's a bit of the history of it, because this isn't just something that is a bunch of farmers, and I grew up as a farmer in the Cotswolds. One of the things that concerns a lot of people involved in farming is it's a new fad. It's not been around very long. Let's leave it a century or two until it's grown up and actually knows what it's doing. But of course, the Chinese were producing rice in paddy fields even before that time, and there is even evidence that Aboriginal paintings in Australia show that the Aborigines were actually guiding water in arid areas where they could grow green food. The real big change in modern time is really down to the fact that LEDs came along, and we went from this thing in the middle, which was an incandescent light bulb, which, while very energy efficient in the fact that it turns all of its energy into something energy-wise, not very energy efficient when it comes to producing light for plants. And of course, the market was primarily looking at high pressure sodium and large halogens. The picture on the right is something that that I did back in 2006, 7, and 8. And the picture here you see is from 2008. And this is actually at Malton College in Northamptonshire. And you'll see that there are some very simple light bulbs. And they were, in fact, the very first LED light bulbs that were built specifically for growing foodstuffs. So it was quite a journey to get them. They're all mains-driven LEDs. They came from Korea. I flew to Korea. I met up with a company in Seoul. They then flew the LEDs out to China. I followed them in on another airplane. A company in China then put those LEDs, they all thought I was mad, into some screw-in light bulbs. And what you actually see there is 3, in effect, cannabis growing tents, because nobody was really doing any of this stuff back then. And there are 4 foot by 4 foot panels of plywood, and just outside there are some standard household dimming switches, so that we could actually control the intensity. So each one of them is equipped with some blue light and some red light and some green light, because we were still looking at RGB as a source of light, because that's really what was available in those days. So that was really probably the very first commercial trial here in the UK. And then of course we've moved to something, and you can see our product on the bottom right hand side there, something much more interesting. So what did we get when we started messing around, and why were we doing it at the time? These are close-ups of those 3 chambers, and in here you can see, very poor, excuse the blur, that's how old these pictures are. In those days we didn't have any pixels. And you can see the product on the left. We just grew this one at an extreme, 100% red. and we got a very leggy, very stretched plant. And that sort of kind of went against the thinking of shade avoiding plants, because if lots of red light's getting through, shade avoidance shouldn't be an issue. They should be really nice, short and stubby. And why were we actually looking at this crop? This is coriander. This was at the time, the largest, and they still are, the largest producer of salad crops in the world, a company called VHP Vitacress. And they had a problem getting coriander into an 8-inch plastic tube to hang on the shelves in supermarkets. You've all seen these little things that they hook them on. And for a part of their season, they get a lovely crop that fits in beautifully. And then early on in the season and late on in the season, it's either too short or too long to fit the pack, and you end up with a lot of stem and hardly any leaf, where you get a lot of leaf in a short, compact plant, and it doesn't fill the packet. And of course, the consumer thinks they're being diddled out of a decent quality crop for what they're paying. And I guess if you get them later in the season when they're properly stretched out and there's not a lot of leaf on them, you would. So in the one in the middle is 50-50, and we've got a squat plant, fairly normal, but they wanted them a bit more bushy, and you can actually see very badly in these pictures, but 50% red, 50% blue, 50% FR. That doesn't add up because that's 150%. But actually, it's because it was so primitive what we were doing. What 50% means is half the dimmer. So that's really where we were at the time. And then I got involved with putting one of the first real sites in, which was in Sutton Bonington, here, right next, just down the road here in Nottinghamshire, where they did a lot of trials and started to move the projects further on. Today, of course, we're equipped slightly differently. I think we built that whole system for about 300 or 400 quid, plus my trip to Korea and China. And here we're looking at a piece of equipment called a Lycor 6800. If you've not seen one of these things, this is actually on a project in Wales, which is why I picked the particular picture, and it's looking at strawberry plants. And what this machine is capable of doing is looking at how the plant is surviving, what it's actually doing, its transpiration rate, how well it absorbs CO2, how quickly it will absorb it, and what it's doing under different types of light. And in the head of this thing, and it looks a bit like a funny looking car vac, but at 85,000 pounds, it's not. And what it's actually doing, it's got a little cup on the end which seals the leaf inside, and depending on the number of tests you're running, it'll do several hundred different tests at the same time. You can do a test in a matter of seconds, or other tests can take up to 2 or 3 hours. Typically, we're looking at about 45, 50 minutes for something that's fairly intense. We can measure them at night and measure them in the day, and we take multiple recordings and data of different types of tests using this device and others. And the reason we do this is because we need lots and lots of data. The good old days in farming, we just look at a plant, is it doing any good? If the soil looks dry, we add a bit of water. If it looks like it's hungry, we add it to give it some nutrient, and theoretically we'll end up with a plant. But as you look at this particular plant, I can see there are 3 different leaves here. And if you look at the leaf at the very bottom, it's quite dark. The leaf that it's actually clamped on is somewhere in the middle. And you can see the newer leaf in the middle, which is very pale in colour. So here we're also looking at chlorophyll, the rate at which the plant's growing. And we do these tests regularly, and that will give us plant performance under different wavelengths of light. You'll see the little thing on the top with the red knob on it. That's actually just a cover. That's a quantum pulse spectrometer sitting in the top. And what we can also do is change the head and put a transparent one on. And we actually do measurements under the light to confirm that the light that's been chosen for the particular plant at the particular part of its life is actually delivering what we were hopefully expecting. So I'm going to talk very quickly about PAR, and a thing called quantum PAR and CIE. This is one of, when you're looking at lights for horticulture, one of the big mistakes is if people start talking about lux or they talk about PAR. And unfortunately, today we still teach PAR in our universities and schools. And PAR, if you've not heard it before, is photosynthetically active radiation. Pretty much all the energy on Earth comes from the sun. And if you look at the blue line, this is what they call the McCree curve. This shows what plants can use in the light spectrum, more or less. There are some debates as to about how accurate that line is, but reasonably accurate. The red box the square is what we call PAR. So you can see that above 700 nanometers, we measure wavelength in nanometers, there's a chunk of light within that blue spectrum, that blue line, that's not included in PAR. And there's also a chunk below 400 that's not included in PAR. And 100 plus years ago, when we came up with this idea of PAR, calculating the different intensities of light to wavelength and the response to the plant was nigh on impossible. You would need an awful lot of abacus to sit there and calculate this thing called lambda at every single wavelength. And if you dim it, or the sun's coming over and the clouds are getting in the way, the calculation would change instantaneously, and you'd never keep up with it. So we came up with the idea of PAR 100 odd years ago, and everything that's in there, in that box, we'll say is equal in giving photosynthetic energy to a plant. And as you can see from the blue line, they're not entirely equal, but it's close enough to give us a reasonable idea that would last for the best part of 100 years. If I look back to that image you saw a minute ago on those plants, you realize that giving lots of red gives you a big, long, gangly plant. If we only gave blue, it gives us a really short, stubby plant. And that was the answer for the coriander back in 2008. But for a single greenhouse, putting in light bulbs was going to cost in excess of £2 million. And it just simply wasn't worth it. We also know now that we can grow under the light that's above 700 and below 400, and we don't have any light at all in the middle. So we could actually grow in one of our chambers just using the light that's outside the box. We can control the morphology, the shape of the plant, how tall it becomes, how many leaves it gets, how much color intensity is in its leaf through chlorophyll, photosynthesis, how crispy it is, and we can also control its flavor. More recently, we've discovered that by balancing red light, which is around about the 700 mark, and then what we call far red above, by balancing those two, we can control the morphology, and then we can actually use blue on the other end of the scale to force growth. And that means we can get a compact plant that's really dense and actually increase the yields. And those are the things to farmers which are really important. And the irony in this is you can actually turn up with a PAR meter from your studies and stick it in the chamber, and you'd actually get a reading of 0, or pretty close. And that would tell you there's no light there for the plant to grow. So quantum PAR is where the world is going. And people talk about how much light intensity they need to grow plants. So really, with 21st century mathematics, we can look at how much light is delivered. And this is the thing called daily light integral. So to explain daily light integral in its simplest possible terms, imagine going outside tomorrow morning with a mug and it's pouring with rain, absolutely chucking it down in bucket loads. And each raindrop, we'll call it a photon, a piece of energy from the sun. So each raindrop pouring into that mug, it would fill up pretty quickly, in probably about 10 minutes. The next day, we take the same mug out and put it on the ground, and we're getting a gentle drizzle all day. And in a 14 or 15 or 16-hour period, that mug still fills up. So understanding daily light integral is how much time the required light is delivered in. So you don't necessarily need to be as bright as anyone might think. It's about delivering enough energy over the growing period for that plant, the time that it's actually photosynthesizing throughout the day. That doesn't mean having super, super bright lights on for 10 minutes in the morning, because the plant simply couldn't process it. You think of an athlete, they need to take in proteins and carbohydrates throughout a long period of the day to keep themselves healthy. If you sat them down in the morning and said, here's half a ton of food you need to get through it for breakfast, they've got no hope in hell. So really that's about understanding daylight integral. And it's a really important thing that is involved in not only controlling the growth rate, but also the morphology of the plant. If you grow a plant too fast, it becomes weak, and then it's not sustainable as a product. So if you're growing salads and you grow them too fast, you don't sort out the DLI and the balance of the available amount of energy that's there for the plant in any one day, what you'll end up with is a floppy plant. It's poor in color. It won't be that fantastic in taste, although you can actually create taste by just making herbs certainly angry. And you can do that by changing the nutrient or turning the lights on and off, or adding something nasty to the water that they don't like, and their defense mechanisms will actually generate more taste. But the biggest thing to your crop is you need to be able to sell it. And if you're selling your crop and it's going to be washed, if you created a weak and a poor crop, it won't make it into the plastic bag. It'll just get rejected. So there's a lot to talk about and a lot to think about when you're looking at light and daily light integral, the type of light, and quantum palm. And that really rolls into your business story: OPEX, CAPEX, and yield. There's a lot of talk about going for high levels of automation. That doesn't reduce your OPEX cost. What it does is increase the salaries, reduces the number of people employed, but the people that are required to operate it cost just as much. So OPEX is about thinking how you can actually produce food through a 24-hour period. And that might not be growing for 14 hours a day and then harvesting once a day. It might be harvesting 3 times a day and actually having 4 harvests running all at the same time in the building, but in different time zones. So midnight to a vertical farm doesn't necessarily have to be at midnight. It could be at 3 o'clock in the afternoon for a certain amount of the crops. So you're spreading your ability to produce over a 24-hour period now, not just 12. And by creating the yield, you're actually paying back that CAPEX much faster because your system's working around the clock. It's not just doing it in normal working hours. So you start to assess the benefits of the crop you're actually growing. You need to look obviously at the vertical farm, container, grow chambers. Are you doing it in containers on the ground? And if so, that's probably for quite a small market. Containers certainly wouldn't be viable for something as big as supplying a packer for a supermarket. They want large volumes and they want to be able to pick it up from one place, not from a dozen or more. If you're growing in a vertical farm, how far are you from the local supplier, the local packer? And do you have enough energy to do that? Glass houses, something that's traditional. We're used to seeing glass houses with sodium vapor lamps and high pressure and halogen lamps. And in reality, we're now actually looking at solutions where we don't actually put any of those big lights in at all, but we're using lighting in between certain crops like tomatoes, cucumbers, and only using it as the plant grows. So again, reducing energy costs. And in polytunnels, we're now looking at systems that will deliver increased yields inside polytunnels. So you don't necessarily have to put up a multi-million-pound building. There are ways of actually using the technology that come from the multi-million-pound buildings in those polytunnels. And we're working with a couple of very large growers here in England at the moment, down in the Vale of Evesham, on a project precisely for that. And just by putting in a system, we're increasing their yields by getting rid of tractor tracks and things and being able to grow throughout winter. So where normally they'd see a season that's only 3 or 4 months long, we're able to stretch that out to 10 or even 11 months, and possibly even 12, which would mean there'd be no importation of crop anymore, and they'd be able to grow sufficient to provide their own pack house. Calculating the ongoing costs, we can help doing that by assessing all of the operational costs and looking at how much yield you're going to produce, where that crop's going to, and the value, and forecasting those things. We've done an awful lot of this stuff with our clients, and we like to be able to help out where we can. A lot of people will talk to you about adding water, CO2, temperature, and humidity, and they sort of limit it. And it's amazing how many scientists that I talk to will talk about closed environment agriculture, and they'll talk about CO2, temperature, humidity, and that's where it stops. This is something that we developed here at LST. It's called the Ball, and we're working with a couple of universities who are helping us with some stuff inside this. And if you look inside that circle, there are 9 cardinals of life, and these are really important. If you don't understand the 9 cardinals of life and how they work and how they interact with each other, you're pretty much stumped. Farmers typically do this instinctively, and they'll stand there and look at the weather and whether it's warm, whether it's cold, and so forth. Once you get inside a closed environment, having precise control of this is really useful. So let's start with light at the top. The dark blue ones are the air zone ones, and the green ones that are dark green at the bottom are obviously the earth zone, or growing mediums, not necessarily earth in modern growing. So light at the top, we look at the wavelength of light, the recipe that you're actually going to do, your choice of that. that gives us the light recipe, and that's a provision then of light for day length. And then we can choose our day length integral. Remember, we don't necessarily have to have a lot of light to achieve a DLI. Once we achieve the DLI, that's controlled by how much intensity that is available, but it's also controlled by how much the plant can absorb in any one day. Having lots of light doesn't necessarily mean we're going to get best value for money from the energy that you're burning. It's important to get that balance correct. CO2, lots of talk about how energy is used by driving CO2 in, so that the plant's going to take in that CO2 and lay down carbon structure. But we also have to think about what's the plant's producing, and that is the oxygen. And if the building becomes oversaturated in oxygen, it can't actually continue to grow and use that CO2. So also the airspeed is important. And the second you start messing around with the airspeed, you start to change on the other side of the ball, the air temperature and the humidity rate. And one of the things that is a little bit frustrating when you see the projects for the first time when they're coming in is lots of people put a huge, great big HVAC system, heating, ventilation and cooling. Works fabulous in offices. It's hopeless in a growing environment, because it's got this vicious cycle inside between cooling and down the air that's coming in and dehumidifying it to only heat it up and then add the humidity again. And that's huge amounts of energy being wasted. And one of the largest sites in the UK with over 3,000 square meters doesn't have an HVAC system at all. It just moves around 32 cubic meters of air every second. And that's equally distributed at the correct speed across the plant. Most of the science you look at will tell you that the speed going across the plant should be 0.5 meters per second. The problem is, if you actually go back and find where that number came from, that was based on a survey back in the 1970s that was required to identify the evaporation amount of water from a bare field and then its equivalent on a grass field. And there are obviously a lot more grass leaves on a field than there are, for example, if you were growing leeks. So the reality of it is you've got to think about the product that's actually there. 0.5 meters per second is correct for grass. And oddly enough, the evaporation and transpiration rate from a field of grass is pretty much the same as the evaporation rate from a plowed field. However, that doesn't work when you start to grow lettuce, chard, and so forth. The leaves are a different size. The leaf on a Swiss chard would act like a huge big sail in 0.5 meters per second. Strawberry leaves move quite hard at 0.01 meters per second. So you've got to get the right airspeed relative to the plant. And we do that kind of research in the lab that enables it. Nutrient, typical behavior from farmers is we put nutrient on because the nutrient man says this is what your soil sample says you need. And we don't then monitor it any further. And we need to, because the plant uses different nutrients throughout its life. As it grows, becomes a plant that is producing a fruit or a vegetable, and that constantly changes. So if you take the same nutrient and put it on because you buy it in bulk 3 weeks into growing, and then maybe 2 or 3 months into growing as you're starting to generate your fruit, actually a lot of that nutrient's being waste. So what we actually do now is we monitor the nutrient use almost on a daily basis. And to do that, we needed to develop some new sensors, and I'll come to those in a bit. Water, obviously, in the ground is a really important thing. And root zone temperature is obviously as important as air temperature and humidity above the ground. That will decide what part of the year you're going to be able to grow in or not. But what I want you to do is take a holistic view of this circle that's here. We call this the ball or the bubble. And the title of this when we developed it was Keeping the Ball in Shape. If you can imagine any one of these 9 cardinals, and they're not equidistantly spaced, they're scattered around the ball. If you were to pinch that ball and pull one, i.e. reducing the volume or quantity of whatever it might be, or push it with your finger, you've effectively changed the shape of the ball. You have to ask yourself then, what do the other 8 cardinals have to do to put the ball back in shape? And this is where, in the past, we have some disasters in glasshouses, and we've seen it again in closed environment agriculture. So typically, if we see a plant looking a bit floppy and that stick your finger in the soil, it feels a bit dry, we add water. Common sense sort of thing to do, really. Actually, what we've just done is condemn that plant to death, because already the damage was done in the root zone and the roots were already retracting. And the problem wasn't that it wasn't getting enough water or enough nutrient, which we've just poured lots in. We've got some dehydrated nutrients sitting in the soil. We've saturated it with lots and lots of nutrient. And the rot that was going on, we've just aided the bacteria and so forth and the fungi to increase that. What we might have done was increase perhaps the humidity in the air zone. And that would have actually slowed down the transpiration rate, the evaporation rate, because air can't take water if it's already wet. So therefore, there are lots of things to think about when all of those 9 cardinals are working together. And to do that, we needed to go into building things like new sensors. So this here says, thank you, any questions? But we've got a bit of an annex. I'm going to flick through it quite quickly because it's going to help you sort of think about questions. And future presentations that we're going to put together as a package, and your team is more than welcome to dip into them, is how light's measured, how light works with plants, the difference between PPF, PPFD, and lux. There is no online app that lets you measure that and convert it. Anyone that tells you they've got one simply isn't telling you the truth. You need a really serious bit of kit, and we have, I think, the only one in the world, certainly the only one in the UK, which is a spectral photogoniometer. It's the only one that's been built, to our knowledge, that actually does all 3 simultaneously, and therefore we actually get an instant comparison. So comparing lux and PPFD, mapping of light for perfect recipe. Having the right amount of light is one thing. Can you actually get it evenly to your crop so that you can actually commercially harvest it? Nutrient systems, nutrient balance, whether it's a nutrient film technique, deep water, ebb and flow, and how those affect the choices to the crop that you're actually doing. Power, huge consumption required for a vertical farm. That's why we try and spread things around 24 hours. And obviously the climate control. Creating those perfect recipes, just very quickly, you can see a nice healthy crop of salad on the left. You can see it's very flat, and it has to be flat because if you're going to commercially harvest it instead of with a pair of scissors, you've got to get light distribution correct. What you can see on the right-hand side is the only 22-meter tunnel in the country that has a quantum PAR spectral photogoniometer specifically developed for horticulture, and that's my hand in the middle in our lab. And I know there's an invitation going out to you all to come in September and have a visit. This is future-proofing your investment. This is the thing we call in-house. I'm not supposed to use its name outside, but they've not come up with that other. We nicknamed it SmashBot. It's one of the smallest and the most accurate sensors in the world at the moment. It's a project that's come through UK funding, which we've obviously supported the funding and developed this. It doesn't really look like this, and the sensors are there just to fool you, to fool anyone looking at it. But the only sensor that's real on there is the one on the top, light sensor, and that is a full quantum PAR spectrometer. And it's to give you an idea of the scale of this. That's the size of the little color tip you get on top of an HBD pencil. So the whole sensor array for 9 cardinal sensors, which is completely wireless and geolocated through satellite, is only about the size of a cricket ball. Typically, this kind of array in a glass house would stand about 5 feet tall and stand on a tripod and be 2 or 3 feet wide and be all lots of boxes and wires. This links to our in-house AI, which at the moment, as far as you know, is the only one that's actually capable of tracking any data and delivering what it says on the tin. So we're linking all of that data in for you guys as time moves forward. Our partners at the moment, Nottingham Trent University, Sutton Bonington are just coming on board. Smart Park in Derby is a government-funded project where they're actually building a mini city based around closed environment agriculture, and we're one of the leads in that. Obviously, we're members like yourself, I think, of the Association of Vertical Farming, UK Urban Agritech. We have a very close relationship with Enzies Arden, one of the largest seed companies in the world, and they have probably the most important food seed bank in the world. It was put together after World War II, and they work with us. Agritech, University of Derby, we have a genomics department there. We work with, we help them actually set that up. GrowFoam is a company in Holland that makes growing materials, and we're working with other companies on those. And of course, UKRI. So there's a lot going on at any one time. And there's some of our team. Simon Deacon is the chief exec, Andrew, who's chief ops officer, our national accountant, Rob Ayres, Andy Williams, marketing analyst, Lindsay is the person, if you're ever calling us, you're likely to get on the phone. Craig and I work very closely together. The lunacy that I create, he has to go and build. Lucy is a design engineer, and the ugly fellow on the bottom left is yours truly. Thank you.
Well, thank you so much for that, John. That was really interesting, and I'm incredibly grateful for that, especially based on the fact that what you've talked about is really quite advanced information that you managed to convey in a really understandable and approachable manner. So it's a real skill to be able to communicate this kind of heavy material in such a way. So very well done, and thanks so much for that. If everyone can think about any questions that they might have for John, I'll just start one off, which is just about with a lot of sort of CEA systems that are currently on the market and devices that people currently use with light timing. It's very much sort of a thing that that the timer will have 16 or so hours or whatever it is, and they'll snap on and they'll snap off. And at no point, it's the discourse is beginning to sort of change into a bit more of how can we match sort of the dawn and dusk phases that plants will have adapted to, with sort of different kind of wavelengths at the beginning to have a light adjusted and then a dark adapted phase at the end. I was just wondering if you could offer any insights as to this sort of dawn and dusk, and what sort of margins are we looking at? What are we looking at? How important is this, would you say, from a grower's perspective?
I'm going to answer. That's a complex question, and I will answer it as best I can. From the early trials that certainly we were doing in containers eons back, we didn't. If you were growing things like herbs, we didn't see a lot of benefit, or any at all. In fact, in much cases, of adding in dimming. It adds costs, and the benefit, and this is where when we're looking at that triangle of capex, opex, and when you're looking at the investment, you have to ask yourself is, yes, it might be happier for the plant to get some different benefits, having a dusk and dawn effect. What you need to think about when you're looking at it from a commercial point of view is, do I get any real benefit for the extra 30–40% of cost of actually putting that in? And so in growing salad crops, we saw very little benefit at all in putting dusk till dawn in. There are other types of plants where you're growing fruit, for example, where a dusk till dawn may have a positive or negative effect on its growing effect and its yield. Yet, having said that, you still have to ask yourself the question, is it financially a viable request to add it in? It's a nice to have. If you're doing some experiments, I would certainly put it in. We have it in the lab. And to give you an idea, the level we have to go to in the lab to make sure that we can answer those questions effectively, we went to NASA and said, what have you got? They went back to Eric Runkle at Michigan State University, and Bruce Bugby, and they said, yes, okay, this is what we're doing, and this is what we put on the International Space Station. This is what we did with Osram, and this thing called Phytophite. Each one of those light fittings is £1,600 a piece. Then you look at the control systems to do it, and everything else is another 8,000. So in our lab, we have 24 of them. I think NASA has 12. That's the extent we go to be able to answer that question. So I think the question really is, it depends on the crop, what you're trying to grow, and whether you evaluate at the end of it, whether it's worth the benefit of actually putting it in. And you don't, if it's a 30% increase in cost, it's unlikely you'll see a 30% increase in yield for having it.
Thank you very much. That was very interesting, and again, well done for explaining this in such an understandable manner. I've got a question from one of our growers, which it's a good question as well and relevant to this, which is, can you talk a bit about this from Robert Jones? talk about the significance of pulsed lighting, square or sinusoidal, and the duration in pulse lighting. Is this something you've been looking into, and is this something that you can offer insights about?
When you say pulse, are we talking about pulse timing? So on, off,
Yes.
on, off. Right, okay. Again, when you look at pulse lighting, it's about DLI. And the idea is, in the process, is that the plant goes through certain events, and I'm not a plant scientist, we have plant scientists in there, so I'm going to answer it as many in the best way I can. The plant goes through a certain sequence of events throughout its day. It requires a nighttime period so that it can actually regenerate itself and grow. So the theory is, and the pulse thing is nothing new. It was done in chickens many years ago, where they turn lights on, chickens get active, they go and get some food, and then the lights go off, they sit down. They turn that food into something that is food for us. Plants will do pretty much the same thing. It was banned in chickens because obviously for animal welfare reasons, it was unfair to give it a 20-minute day, wake up for 20 minutes until it makes sleep again. Again, controlling and how you produce your crop and so forth, and how you install lights in a building, this comes down to the equation, is it worthwhile doing? Can you grow more crop fast enough using a pulse mechanism that will enable you to only work in a certain number of hours per day? So let me give you an idea on a big scale. This will depend on the scale of the project you're actually running. So if you're growing 50,000 square meters, and I use that number because I've done the maths on it and we've actually put together a project for that. 50,000 square meters of salad crop will produce about 32 tons of food per day, okay? You have a quarter of a mile worth of handling equipment and automation, and that crop's got to keep growing. If you put 50,000 square meters of growing space in, that's an awful lot of power being used at any one time. But what you must do to make it work effectively is have commercial trays of salad, which are 3.5 meters long, 1.7 meters wide. They'll probably carry about 12 to 14 600 by 400 trays on them, and they've got to keep streaming out, because at that scale you're looking at automation, and you've got some skilled people there, and for a certain amount of time each day you're going to have to shut some of that equipment down because you've got food standards state requirements to face. You've got to be able to wash the equipment. The harvester's got to be cleaned at least twice a day. It's got to be cleaned every time you change the type of crop that's going through it, because cross-contamination of different chemicals from different plants, especially if you're dealing with people with allergies and things somewhere down the line. And you want those trays to keep coming, because if you spent £40,000 on a harvesting machine, and you'll need at least 2 on that kind of scale, possibly even a third as backup, those machines have got to be running 24/7 to pay for themselves. Otherwise, you'll never get your money back growing salads. Simply doesn't work. The financial value of crop isn't there. So a farmer, for example, that's got 1,000 acres might buy themselves a big case 4x4 weighing in at 12 tons to pull a 12-bladed plough. But the guy down the road who's got 1.5 acres is still driving around on a Fordson with a 2-bladed plough, because that's effectively cost effective on that farm. So the question really is again, with on and off light, if you're doing small crops, high value, and there is a benefit to them in actually growing them quicker, faster, but you're only going to harvest once a day on a small scale, it may work. Would it work in a 50,000 square meter farm? Highly unlikely. It's unlikely because you're stagnating that movement of those trays. So the whole thing is about, is there a biological advantage in the plant? Is there a practical advantage that actually generates enough income from what you're actually doing? And that's really part of what we do in the lab, is test those theories. So we can run a program in the lab. We can have the light going on and off every 10 minutes, every hour, every whatever time we want to set. We can even change the light recipe through that period. And again, when you're looking at light recipe, could you change different frequencies? Our light fitting can go up to 9 channels. We can dim those 9 channels, change the recipe throughout the day. But you've got to be growing a crop that's worth a lot of money. If you're looking at salads, it's unlikely that's going to happen. And if you look outside the box at some of the medicinal plants we're looking at, 1 milligram of extract from around 500 kilos of crop, which obviously if you can get a building that produces 32 ton in a day, 1 milligram of the chemical that I'm thinking of is $180,000 a milligram once extracted. So you can see there are crops in closed environment that will produce vast amounts of money, but they'll have a fairly small market. And there are others that will take a huge market, but may have a much lower value. And salads typically is where people go because they're relatively easy to grow. But there are crops outside. Again, we're helping to bring closed environment, vertical farmers, even polytunnel growers, glasshouse growers into that environment where we can say, look, why don't you try some of this? And there's a bit more money involved in it there, so you can gain your money quicker.
That's again really, really interesting answer. Thank you very much. Does anybody else have any questions from anyone else in the audience? We can ask John.
I'd probably like to just pursue these light recipes a little bit, if that's okay.
Light recipes.
Not trying to delve into your IP.
No.
I just
anyway. I'll answer it with a funny story, really. In 2017, I was asked to go and speak on light recipes at the World Innovation Conference for Lighting for Horticulture in Eindhoven. There were 60 representatives at the time, not us, we weren't there at that time. There were 60 representatives of lighting companies, all of which had a lovely sign on their stand saying, we will provide you with a perfect light recipe for your crop. We already have these light recipes and they're proven. What they didn't know was I was just going to be the spanner in the works that day, because the person who was organizing the event was really annoyed at so many people saying they have a light recipe. So I stood up, held up a very big check and said, in my opening sentence, said, anyone in the room who actually has a light recipe, they can back it up with scientific and repeatable evidence. This check is for you as a bonus. No order required, just the bonus. And it was a very big check. My wife was sitting in the front, absolutely terrified that someone would put their hand up. But I was fairly certain that no one could, even though every single one of them had an advert up saying that they got recipes. More and more recipes are coming on. And if we go back on the market, people are putting IPs and things on. And this is where it's important to work with teams like we have to make sure that the recipe of light that you're using suits the environment that you're growing in. Because just because someone's growing a particular lettuce and the nutrients the same, the temperature's the same, the humidity's the same, the spacing of the light would need to be precise. The building would actually need to be a clone of another building where a recipe works to make that recipe works. And even then, if the water quality is different in that same place, that recipe will change. Each and every environment, no matter where you are, requires that holistic view of that ball to understand what is the best recipe for that crop in that environment on any individual day. And that's why we looked at creating Smashbowl, because that environment will change. If tomorrow you've got 40 visitors coming through your site, the CO2 level will change dramatically. And that will move everything. I'm sure you've all walked into a container and then watched the CO2 spike when you've come out looking at your references. When you're looking at recipe, it's important to find the type of recipe. And again, can you afford in the crop that you're growing to be able to change that recipe? One of probably, and again, I have to be careful, not so much our IP, but obviously when we work with clients, we work under an NDA. But one of them at the moment is looking at being able to change the lights quite frequently for different types of season. And that's where our development of light is, that we work on the basis that the development of the light is 80% our manufacture, then 20% is the client's. So the end fittings, the light inside, the recipe, etc., and so forth can be changed. So actually we can dismantle our lights, take the circuit boards out, store them safely, and put different ones in for them to grow a different crop at a different time of year. And then come around, they'll swap them over and everything else. They don't need to go and buy new lights. Or again, evaluation of whether it's financially viable to have a tunable light. As I say, we've got 9 channels in our system, so you can actually have them in. And they're probably more likely used only in research rather than large production. In time, as cost of LEDs and production comes down, they'll get closer and closer to being usable. There are different recipes for different light. And at the moment, we're running a project in the lab. We've got 2 or 3 running, but one in particular is very interesting, where we're looking at different recipes of lights on a fruit product. And some of the results are coming out frightening. They're certainly not what was going to be expected. And in the one which we thought was going to be the one most extreme, actually is the highest possible yield. Never seen this plant grow like it. They're outgrowing the chambers, leaves on them, they're just enormous. So you expect something about the size of the top of a mug, and they're like 4 times the size. And the fruit yield on them is much, much higher. And you would have thought that would be completely the opposite to what anyone was expecting. So as for recipes, if anyone tells you they've got one for your crop, take it with a pinch of salt.
I think some of what I was interested in, you definitely covered. So for cheaper or for less capital intensive setups, and you have a kind of a fixed board in there with a fixed recipe, but then at the other end of the spectrum, then you have a tunable recipe for that research situation, I guess.
Yeah, and again, what's really interesting is people will tell you, don't go red and blue, don't go red and blue, you need some white, you need some bits and pieces. And at that particular conference, I was asked the question at the time. And of course, there's a change in thought in the way, and of course, the efficacy, energy-wise, of the LEDs has changed since 2017 quite considerably. So why do we put white light in, or why do we put green light in? Well, if you're using red and blue and you add green, you get white for human vision only. So it's helpful for the operators to be able to see their leaves. But for energy efficiency, if you're literally coming down to the crudest limits of actually how can I grow product and make it most energy efficient, then you want to go for a blue and a red and forget white and green and put a torch on your head, because you can recharge an awful lot. You can recharge an awful lot of batteries for the thousands and thousands of pounds you'll save by not putting in other colors. Do you need those other colors? Absolutely not. Can you grow a crop under blue and red light that is commercially viable, is going to be crunchy, strong, and available? Absolutely. We've done it, and on a large scale. A crop that was accepted by one of the major packers and brands in the UK that you see in every supermarket. So yes, you can grow just on blue and red. Be careful where you buy it from, because if it's a blue and red and it's one coming on a cheap Chinese product, and I won't say that the Chinese make all rubbish, because they don't, because they make some fantastic products. But there is this kind of Western view that you get everything from China on the cheap, and you end up with a product that doesn't really deliver for very long. And that's the issue. They're relatively inexpensive, but they don't keep delivering what you're asking for a long period of time. And they're not particularly waterproof and so forth. I had one sent to us a couple of weeks ago. It came out of the box and the end caps fell off. And that was really quite worrying. And the tube wasn't cut to the right length for the boards that were in there. And you start to look at that sort of thing. And that's a product that's a mainstream product being sold in the UK for a growing system on small scale. And that's really worrying, because for a few more pounds for each unit, you've got something that would last you 20 years. And it seems it's just a false economy. So the answer in your question about if you're looking at recipes, we've certainly built a product for a client that was the right length to fit a very large system, and they wanted to make it the most cost-effective way of growing, and they ignored the white light necessity for humans to see. They ignored all the rest of it. It was purely about photosynthesis, making a light that would grow a good, strong crop that was saleable, and it was the simplest light that they could get, which was a red and a blue. So you end up with that purple light that you see in the back of this picture. But the one in the back of here has got a little bit of white in it as well. So, but you can do all sorts of things with them, and there's a lot of ideas about what's the right recipe, what's the wrong recipe. Don't be fooled by the white thing. The whole white thing that's going on at the moment, with lots of white light everywhere with just a little bit of red in, that's a commercial decision. It's got nothing to do with the plant whatsoever. As we talked about PAR earlier on, the reason they add the red in is because you need that red that's in quantum PAR in growing the crops that they're actually targeted at. But the only reason they're using lots and lots of white is so that they can sell you a product that's lower value in cost. And the reason for that is there are more white LEDs manufactured in the world than anything else. Okay, so therefore, if you could buy a white LED cheaper than a blue and a red and a far red and a green, and produce light that comes in that box for PAR, yes, you'll get growth. Add a bit of red, yes, it might improve the quality a bit, and so forth. it won't be targeted specifically at your crop, and it won't be energy efficient, because the worst energy efficiency comes from white LEDs. They are getting there, but the highest energy efficiency comes from a pure red, a pure far red, and a pure blue, because there are no layers of phosphor laid on them, which obviously is wasting energy. So it's a cost effectiveness thing that you're seeing in the market at the moment. There's a lot of white lights coming out going, hey, you can grow with this, you can grow with this. Yes, you can. But the reason it's cheap is because it's a white LED and you're burning more energy. And what you have to remember is, and this is where your OPEX costs come against that CAPEX in the triangle, is if you've not spent enough money at the beginning to buy a good quality light that is suited to your crop, you'll end up spending more over the lifetime of that product on energy than it was to buy the right product in the first place. And a lot of people don't look at that, because they're looking at their CAPEX right at the very beginning, saying, how cheaply can I build, how most inexpensively can I build this system, because I need to get going and start producing some crop. And it's a pitfall we see a lot of people falling into. But when you sit down and do the long-term math, they go, oh, that's costing me an extra X, Y, Z. So a good example, which came out of that conference, because I'd taken the numbers with me and I remember it off the top of my head now. Somebody said to me, are you going to add any white light? And I said, one white LED in each of these strips will add £30,000 to the energy bill in a 3,000 square meter growing space every year. £30,000 over a 5-year period is an awful lot of money.
It's a lot of extra lettuce you need to sell.
And you just won't do it. So the reality is don't put the white LED in. If you're looking absolutely crucially to growing the lettuce and getting to do it, don't bother putting it in. It's a nice to have. And I think my answer was I could buy an awful lot of rechargeable batteries, stick a headlamp on and go around and inspect my crop without lighting up the whole thing for all of the time for something I'm only going to look at for 2 or 3 minutes in a day. There are crops where white light is useful, and we put small amounts of it in so that you can use it as part of the growing mechanism, and also you might be looking at needing to look at the crop because it's on the move, for example, some of the systems where the crops are actually moving. Hope that answers that one. It's quite a contentious one to answer, but I've tried to give you the most honest answer I can.
Oh, that's great. I think some of the people here know I'm sort of more interested in appliance scale domestic rather than the large commercial operations.
Yeah, well, in which you can buy little kits and grow them in the window, and they've always come with a white light. But if you're sticking it in the window, of course, the plant's getting lots of benefit from the sun, and all of those other elements that are missing are being delivered by the sun, even in winter. If you're going to try and do it on a scale where you're doing it in the garage, then absolutely just go for blue-red. You'll grow crop. If you're going to use it locally in a small scale, you don't need to spend that money. Have an LED white light bulb in the room and turn it on, have a look. If you're doing on a much smaller scale. Becomes more complex though when you start to look at putting in point of sale things, because we have something similar with some of our clients where they're actually building units to go into supermarkets or into restaurants where they're growing some crop and they want to be able to show it off. And we've been doing that for years. You go into the butcher's in a supermarket and you pick up this beautiful red piece of meat. You get it home and you look at it and go, well, didn't look like that in the supermarket. Well, the supermarket knew a long time ago that through customer research, they like to see nice red meat. Get it out in the natural daylight and it looks completely different.
Thank you.
Yeah, I'm really glad I've decided to record the questions. There's some really good stuff coming out of this. And again, thanks for some really good stuff there, John. Geraint, you've had your hand up for ages. Do you want to come in with a question?
Well, thanks, Luke. I'm just picking up on the smart box or smart bots you've got, John. And you mentioned you've got AI linked up to it. So I'm just struggling to think a bit with that. The fact you've got an AI, which I think, if I understand, is there to try and manage the nine cardinals you explained, and at the same time acknowledging maybe we're not fully up to speed with how everything works together within the different environments. I was thinking, what's your approach to train the AI, and which neural networking setup have you approached? I'm thinking because I'm involved in some convolutional neural networks. I was just wondering whether that's getting involved there.
The answer is yes. Can I tell you which ones? No.
Okay. I thought there might be some.
Yeah,
there might be a line somewhere. Yeah.
Really interesting is that when we start looking at farming, everything we do in farming is reactive. So we see something go wrong, we see something changing, and we try and add something to it, or we try and adapt to try and put that problem right. Obviously, if you're growing wheat in a field, that's a lot more difficult because you're pretty much victim to the weather. But of course, even when you've harvested it, you can then take some of it away if you've got the timing just right, and you can help to dry it and so forth, and get that moisture percentage down. If you're looking at growing crops in a glass house, it gets more challenging. And typically, the whole Dutch glasshouse thing is really given as a big example. But if you've ever flown out of Holland in the evening and you see the amount of light that's on in all the glasshouses, you think, what an incredible waste. What most people don't realize is the National Agricultural Bank many years ago did a deal with the government and the energy companies. They put generators into a lot of these things where they're burning gas. The byproduct is CO2. They scrub it to clean it, take the soot and all the other contaminants out, and they pump the CO2 into the glasshouse. The generator is actually running an electric generator, which then sends the energy that it's generating onto their national grid. And they're buying in their gas from their local supplier. As you know, there are huge fuel and gas processing plants in and around the Rotterdam and that area, and around the Hook of Holland. So there's a symbiotic relationship going on between the three things all the time. And in winter, the excess heat that's generated from the generators inside is then used to keep the glasshouses warm. It's a complex way of doing it and not really very friendly to the planet, because in the summer, that heat's still there. And the only way to keep the greenhouses cool is to open them, and hence the term greenhouse gases and all the CO2. They're continuously pumping CO2 in, and then it's escaping. And depending on the crop, CO2 is useful to push it up in some crops. In other crops, it's of no use at all. The baseline of CO2 for planet Earth is about 260 parts per million. We, since the Industrial Revolution, have shoved it up to 400, 450 in that range. And there should really be ample for plants to grow. And if you're changing the air fast enough to take away the oxygen, really the plant can really only process X amount of CO2 in that time, because that's all it can do. And it reaches a point where it won't take any more CO2 in anyway. And those limits have not been defined per crop, per cultivar at all in any way, shape or form. So when you imagine that ball we're looking at, and the different elements changing at any one time, they're constantly changing throughout a day and a night time, we end up with a net result that we see days later. And the farmer looks at it and goes, I'm going to need to do X, Y, Z, add more water, add nutrient, take the blinds back, let more light in, whatever it might be, reduce the temperature, pull the blinds over, whatever the response might be. And that's all reactive. What the AI is doing is actually looking at the trends that are going on in any one of those nine cardinals, and it's learning and understanding by a process of elimination what are the net results of those eventuals. So if you leave something doing that, where does it end up? If you leave that combination of events, where does that graph end up? What it then does is look at all of those trends and then try to neutralize them so that they're actually following a growth graph. Now, I'm going to blow our own trumpet now, and it's not mine because we've got this fantastic team working on this in-house. This was UK government funded or partially funded. We obviously have to put up the lion's share of the money. And to be fair, while we won that funding just over a year ago in COVID, and we sort of trogged on and carried on, we've got a really good idea where we were going with it. And pretty much, I'd say tongue-in-cheek, it was taken tongue-in. It was something that the world needs to see. It was a really serious attempt at having a go at it. And I would say the adjudications and so forth, let it go through. And even our regular guy that's watching what we're doing was a bit sort of, yeah, okay, let's see what, tongue-in-cheek, let's see if we get anywhere with it. I can tell you that MIT's been doing it in the US. I can tell you that some of the universities in China have been doing it. And obviously, in Wageningen in Holland have also tried to do it. I can also tell you that the only one that actually tracks the data is ours. And Can I tell you why? No, I'm not the expert, the genius that does that, but I have really behind us this phenomenal team that have been working on it. And it was a bit of a eureka moment when we took a bunch of data from China, which we knew as factual from greenhouse growing out there, and we ran that through the AI. We fully expected to wander off like everybody else's does. It didn't. There was an error in the data, and it actually tried to put it right. So I'm touching wood at the moment, saying we're on the right track. We're very excited about what's happening. Smashbot, as it's nicknamed, and that was its in-house number. You've seen it looks like the mashed potato head, which is why we call it Smashbot. It will have a proper name as it's released at the end of this year and into the beginning of next. It also comes in bits, so you can add bits in so that the farmer doesn't have to buy the whole 9 cardinals if he's not interested in something that's going on under the soil or in the water, and there are various adaptations. It's got a cup anemometer in it at the moment, but it'll eventually have its patented version has an ultrasonic one. So it'll also give us air direction and speed. So we can put multiples of these in an area, be it in a field, a polytunnel, glasshouse, vertical farm, someone's garage, and we can actually then map where air is moving and whether humidity is changing. And you can see air currents and things moving around.
Oh, great.
Thank you, John. This will then have a control system that will then feedback. We're working with all the majors like Preva and so forth, so that it integrates with them, so that you can add it on to any system. It also uses the light system as a network. Once you get big structures and you get lots of metal, you can't get signals easily transmitted around. So every second data will come out, and if you're in an awkward place, nasty buildings, lots of metal, the lighting network will actually ship the data around and ensure it stays safe.
Okay, thank you for that, John. Yeah, fascinating. Thanks.
You'll see it on your visit anyway.
Oh, thank you so much. Can we take one last question, which will be from Robert Jones, if that's all right? Thanks. You've been waiting very patiently for a while.
Good afternoon, John. Yes, good afternoon, John.
Come
back to airspeeds again. You mentioned that the standard in the 1970 was 0.5 meters per second. You mentioned the Strawberries was 0.1 meters a second. What would the char range be, and what would be the normal range be normally in the CEA system? And also, would the air be horizontal or vertical, turbulent or laminar flows?
Interesting question. It's a tough one to answer in one simple. Yeah, okay. So 0.5 meters per second was grass, and if you look back at that 1970s research, and this is one of the things that the AI is starting to learn now, what is the right one? Because having an AI in situ, what it's doing is measuring what is the net result of an airspeed. Predicting an airspeed over a crop actually would change. So if you looked at the dicotyledon of the first 2 leaves coming out of a Swiss chard, it's not looking anything like a fully grown leaf that could be 30 centimeters long and 12, 14 wide. But the golden rule of thumb is very simple. If you look at the leaf and you get a small amount of movement, you've probably got enough air. If you've got violent movement or lots of excessive movement in any one part of it, you've got too much. And oddly enough, even going back to the grass, 0.5 meters per second for grass meant you had a tiny amount of movement from the leaf. And that really and there are 2 effects to that. No one's really quite sure what the effects of the physicalness of the plant, but it solidifies the structural integrity of the plant so that it's not going to fall over. And that's part of where some of its energy goes. And the question will be is, do you actually want that in any particular crop? So if you're growing a medicinal crop where its rigidity is not required and you actually want as much moisture in the plant as you possibly can, you would probably drop that speed right down and wouldn't be worried about whether the integral structure of the plant, because you're looking at mass where you get chemical extraction. If you're looking at lettuce, of course, you want rigidity so that it's nice and punchy and it survives going through washing. So again, this is part of the research that we're doing now to find the answer. Is there a definitive answer for any particular crop? The answer is no, because no one's done the research. But rule of thumb, small amount of movement.
What about the horizontal or vertical in a CEA system?
Yeah, okay, so this now you're really delving into my toy box. And I'll tell you what I'm doing. We're building a brand new facility just south of Derby, just over £2.5 million building going up just for researching, double the size of our lab. And it will give us also some extra space for developing and so forth. And in that extra space, I'm putting in 2 walk-in chambers as part of the effort from the team that's going in. I say I am, the company is, it's my job to get them built. And I haven't yet found a walk-in chamber that will deliver the answers that I want. So we're actually working with a couple of manufacturers to build our own walk-in chamber, which will answer the question you've just asked, because we are putting a system in that provides air from all of the surfaces. So all four walls, the floor and the ceiling, and we can change direction so that we can identify which is the best solution for a plant. Does it need air coming up from underneath? Does it need it from on top? Does it want it from the left to the right, each end? Does it want changing? And does it need to have some kind of change? We talk about plants following the light and obviously phototropism. We know about gravity tropism. Is there an effect, a tropic effect on the plant as to where the wind is actually blowing? If you look at trees on the island of Jersey, they all look like they're slanting to the left and no branches going to the right. So clearly there is an effect on wind, but what kind of chemical and biological and structural effect does it have on a plant? Don't really think there are enough answers out there for me to answer that question for you at this point in time. Are we trying to find the answers? Yes. Are we building the equipment so that it can be done? Yes. What's his space?
Okay, thanks, John. Very good. Thank you.
Well,
Thanks for the questions, Robert, and very good answers again, John. I think I'll draw the main part of this session to a close now, unless anyone's got any last questions. And then I think we were going to have a short word with you afterwards, John, to arrange a few things. Does anyone have any final questions before we say thanks again to John? Okay, well, that's much appreciated. Really good session there, and I think we'll all be really keen to see this space develop further. And I'll end recording here.